Today. Okay. By the end of this lesson, you'll be able to calculate various aspects of position, time, velocity, something in free fall, and be able to know the fun facts of free fall and how to apply them to specific scenarios. Okay? So, if we took air resistance away, sucked out all air molecules, and we dropped a feather, and we dropped a penny, or in this case, a bowling ball, which one's going to hit the ground first? Okay. This experiment was done in the world's largest vacuum chamber. It's like the size of a silo. Good at that. Okay. So some of you might be like, yeah, that's nice. You can get anything on video nowadays. Fair enough. So in here, I've got a piece of tissue paper, papers, and a penny. Use that. Okay. I'm going to suck out, oops, sorry. Video people. I'm going to suck out most of the air. It's not going to be perfect. I mean, but ready? Got to get rid of static cling. That gets you. Okay, good at that. Oop, video, folks. Okay, so what's that sound of? Air going back in. Good with that? Okay. All right, so fact. All things on or near the surface of the earth fall at the same rate. Does not matter how big it is, does not matter the size, the shape, does not matter the mass or the weight. All things. Elephants, mice, skyscrapers, dandelion tufts will all follow the same rate if we ignore air resistance. Now, some of you might bring up have a qualm about that, like, what? That's so stupid. That's not real life. We deal with air resistance all the time. How can you say that physics is the study of real life and we're ignoring air resistance? Fair. But consider this. Ignoring air resistance is a simpler scenario. Once we understand the simple, then we can add a layer of complexity to like try to understand that. Does that make sense? Turns out that the math behind air resistance is pretty complex. Like it's the last thing I teach my AP physics students, the last thing, because it requires that much math to do. So you're welcome. We're going to ignore air resistance. Okay? Sound good? So, when is something considered to be in free fall? I'm going to suggest this. When only the force of gravity, when only the force of gravity is acting on an object. Okay? When only the force of gravity is acting on an object, we're going to consider that to be in free fall. You all right with that?
Does that definition stand like in real life, taking into account air resistance? So it's like, is anything ever actually in free fall?
Oh, great question. Not on this planet. Okay. So if something's in free fall, only the force of gravity is acting on it. All things fall at that same rate. Well, how do we describe that rate? Is it moving at a constant velocity? Is it speeding up and then moving at a constant velocity? Is it speeding up the entire time? Like, does that make sense? Our choices, like, yes, they all fall at the same rate. Well, exactly how could we describe that? So you might know the answer to that. You might have a factoid, but I want to build a case here. Okay. Do you remember Newton's second law? The net force is equal to mass times acceleration. Okay. So if something's in free fall, sorry, I should have asked this question. Something's in free fall, the only force acting on it is gravity. Okay. So again, just a reminder, this is the total force is equal to mass times acceleration. Okay. How do you think you would describe the motion of something in free fall based on this equation? And this, here's your scenario when something's in free fall. Have a conversation. How would you describe, is it moving at a constant velocity? Is it speeding up and then moving at a constant velocity? Is it speeding up the entire time with a constant acceleration? Yep. How would you describe how something moves when it's in free fall? Okay. If okay, so let's do this. Let's say I was in deep outer space and I had a ball and I let go of it. What would that ball do? Just stay at rest. Its inertia wants to stay at rest. It's at rest. They're like, I'm good. Okay. If you throw that ball, what's that ball going to do? Keep on moving at a constant velocity. You all right with that? That's what its inertia wants to do. Okay. We're here on Earth and I drop something. Did it do what its inertia wants to do? No. Why not? Because gravity caused it to experience what? Acceleration. Does that make sense? Okay. There's an unbalanced force not doing what inertia wants to do. Its motion is being changed. Okay. So, the force of gravity acting on an object causes it to experience an acceleration due to the force of gravity. Okay. That acceleration has a value of 9.8 meters per second squared. And what do you think that negative out there represents? Why is it downward? It's the same direction as the force. Okay, the force of gravity is acting down, therefore the acceleration it experiences is in that same direction as the force downward. Okay, this, real quick, folks, this is not a force. This is how something moves because of that force. Does that make sense? Okay, this is the motion. Everything dropped will experience this acceleration. Elephant, mouse, doesn't matter. Good? Okay. So, for these types of questions that we do in class, I'm going to round this to 10 meters per second squared. But on homework, on labs, on tests, use 9.8 downward. Okay. But this is just for mental math sake. Thumbs up when you have a guess. Have a conversation. When did you want to make up that lab quiz?
I won't be here tomorrow
You
because I have an appointment in the morning.
Okay. So no study hall.
I do first period.
Bummer.
Yeah. I don't know when I'll be back. It'll be around like 8 or something like that.
Okay. Doesn't take too long. You can do it now. You can do it after school. You can do it. I mean, I guess we could do it first hour on Monday, but I don't know. Are you going to remember?
Probably not.
Yeah, I don't think so. Okay, what do you think about that?
Okay.
Correct answer is D, 50 meters a second. Dangerous dinosaurs. 10 meters a second, 20 meters a second, 30 meters a second, 40 meters a second, 50 meters a second. Every second that goes by, you're changing your velocity by 10 meters a second. Good with that? Have a conversation.
Oh, yep. Either A. But that's just the acceleration. Yeah.
Oh, you need that. I will eventually.
Starting the clock as soon as you drop it, or you start it. So,
Okay. Everybody have a guess? What do you say? We're going to find out. Okay. So, what variables do I know? No time. What else? Okay. If something's in free fall, I do not explicitly need to tell you that the acceleration is equal to 9.8 meters per second squared. There's very few things I'm going to tell you to memorize. This is one of them. Okay. What else do I know? So what? I do know x initial. I'm just going to say I'm looking for displacement overall. I need one other. Initial velocity is equal to 0. If you drop something, we're going to assume it's from rest. You remember the skydiver? The unfortunate skydiver? Okay. Start at rest. Good with that? Okay. So here are our variables. How would you describe the motion of something in free fall? Is the velocity constant or is it changing? It's changing. So therefore, what equations should we use? Kinematics. Okay. Now, what I want you to do is I want you to pick, don't tell. But I want everybody to pick which equation is appropriate for this scenario. Tell your neighbor. Correct answer is third one. Okay. So I'm going to write my original equation before I stick in numbers. Okay. My initial velocity is 0, so that knocks that part out. So I have 1/2 times negative 9.8 times 3 seconds. Square it. When I do the math, I end up with a negative 44.1 meters. Okay. What does this negative sign communicate? The direction of downward. So, I guess, sorry, I didn't specify this. When we're talking about free fall, up is the default direction, positive direction. Most people don't have a problem with that. Okay. So the fact this is negative means it's going downward. Okay. Now, well, I guess before this. So did we see that free fall is just a special case where we can employ and use the kinematic equations? There's nothing really new. It's just a scenario where this is applicable. Good with that? Okay. Now, check this out. Register that. Previous question. Correct answer is C. Okay. Here is why. Do you remember the acceleration in the alley? Okay. As you sped up, the displacement, let's say the acceleration was 10. Talking about this. Okay. In the first second, the 1 Mississippi, you'll go 5 meters. Okay, less than 10. Okay, that's because you started at rest and ended up going 10 meters a second after 1 Mississippi. But then 2 Mississippi, you're going from 10 meters a second to 20 meters a second. And you'll travel 15 meters, like up to the 15 meter mark at that point in time. Then going from 3 Mississippi, you're going from 20 meters a second to 30 meters a second. So you're traveling a whole lot further distance. Does that make sense? Okay. And so that's why it's going to be more than after that 1 second, it kind of like the speed increases. And so we would expect the position versus time graph to look something like that. Does that make sense? Okay. Good? Okay. All right. What is the condition for something to be in free fall? Only gravity's acting on it. Okay? When something's something's going up, is gravity the only force acting on it? Okay. Oh man, let me get closer. Okay. Right here, when I let go of it, I'm no longer exerting a force. That'd be really stinking cool if I could. Jedi stuff. It's a bummer it doesn't work. Okay? The moment I let go, the only force acting on it is the force of gravity. You okay with that? So, as something goes up, is it considered in free fall? Yes. Gravity is the only force acting on it. Okay, so in physics, we consider things that can be going up and still be considered in free fall. You all right with that? Okay, so here are some fun facts of free fall. So we're ignoring air resistance. These are the conditions. If I throw it at the same height at which I catch it, or I catch it at the same height as which I throw it, then the time up equals the time down. This experiences constant acceleration. Okay, time up is equal to time down. Fun fact of free fall. These three fun facts, memorize them. They're very helpful. Okay, time up is equal to time down. If caught at the same height as which it was thrown. And ignoring air resistance. Second fun fact. If I throw it at 20 meters a second, I'm going to catch it at 20 meters a second. The velocity going up equals the velocity down if I catch it at the same height at which I throw it. Okay, ignoring air resistance. That goes out the window if air resistance is a thing, which we're not going to play that game yet. Good with that? Okay. Question. Thanks, sir. Good. What? Yeah. Okay. Tell your neighbor. Correct answer is? Correct answer is A. Okay. The turnaround. Have you ever been standing on some elevated position, whether it's like a roof or a ladder or a treehouse, and someone's thrown something up to you, and it was like a perfect throw? Like the object just like comes up and is like just hangs there. You're like, oh, thank you. Try it. It's pretty cool. Okay. Slows down at some point. It stops to turn around. Okay. 3 fun facts of free fall. Time up equals time down. The velocity that you throw is the velocity at which you catch it. And the velocity at the highest point is equal to 0. Fun facts. 3 of them. Good with that? Okay. I'm going to tell you the answers to this. So I don't want people getting confused. Okay. We are looking at the scenario when it's in free fall. Okay. Only the force of gravity is acting on it.
Got your mail. It's trash.
Perfect. Gee, did I win? When the paintball is in the barrel of the gun, there are other forces acting on it besides gravity. That is not free fall. Okay? So we're not looking at while it's in the barrel of the gun. We're looking at right as it leaves the barrel of the gun. It is moving at that moment in time. Okay? We will deal with in the gun later when we know how to do some more stuff. But right now, we're just keeping things simple. It's just in free fall. Only the force of gravity is acting on it. Okay? So the initial velocity is going to be 22 meters a second, not 0. Okay? In a similar fashion, at the end, it still needs to be in free fall. Okay? Only the force of gravity is acting on it. We are not looking at it after it's like splatted on the head. We're not looking at after something has like embedded itself into the ground. That's not free fall. Okay? We're looking at it like nanoseconds above the ground. It is moving at that point in time. Okay? Correct answer is D. Dangerous dinosaurs. Okay? This will trip you up a lot, some of you. I will ask this question frequently. If I dropped a bowling ball on your foot, would it hurt? Yes. Why? Because it's moving when it hits your foot. There's motion there. Okay? Does that make sense? We are not looking at it after it has embedded itself into your foot. We're looking at how fast it's going when it hits your foot. Like at that exact moment, it was like, whoop, moving. Everybody good? Okay. An arrow is shot straight up. At the highest point, it reaches a height of 70 meters. Assuming it was shot from the ground, how fast was it shot out of the bow? Okay. Awesome, Smiley. You gave me one number. Thanks. Appreciate that. First thing, draw a picture. Okay. What numbers do I know? What? We know acceleration. What else do I know? Displacement. Now, where's the arrow located? What's the position when it's 70? Where is it on this? Up there. Does that make sense? So check this out. I can make the final location at the highest point. But it doesn't stop there. You're right, it doesn't stop there. But I can make the initial and the final point anywhere along that experiment. Sorry, anywhere along that motion. Remember the fan cart lab? Okay. You could pick the initial and final to be anywhere you wanted to. Anywhere along this line. Here, so long as the final comes after the initial. You have that power here. You can pick anywhere along here to be your initial and final. I'm pick here because I know something about it. Does that make sense? I'm not saying the arrow stops there. Just saying I'm done evaluating the scenario. Okay? So what do I know happens at the highest point? Your vertical velocity is equal to 0. Fun fact of free fall. Huh, look at that. Okay? And I'm looking for my initial velocity. So, go shopping for an equation. Thumbs up when you have one. Tell your neighbor. Correct answer is equation 4. It does not have time. It has all the stuff that I need. Or sorry, it has all the stuff I have and need. Rewrite the original equation. Plug stuff in. Do some math. Find that to be 37 meters a second. Okay. Sorry. So when I take the square root in math class, technically what are we doing? What's the answer in math class? Plus or minus. Okay. That has significance in physics. Which one are we going to choose, the plus or the minus? Why plus? It's going upward initially. That makes sense? Okay. And on the way back down, it'd be going negative 37 meters a second. See how that works? Okay. Now, before we box that answer and it's like, yep, we're done, take a peek, make sure this makes sense. Could an arrow be going 37 meters a second? Okay, here's just a rough connection with miles an hour. If you double your meters per second, that'll give you roughly your miles an hour. So roughly 80 miles an hour. Is that realistic for an arrow? Fastball is 90. An arrow? Yeah, I think we can make an arrow go 80 miles an hour. Okay. Good with that. Okay. Have a conversation.
How can atoms ever touch?
Okay, hang on to that thought. Okay. Correct answer is A. The moment it leaves my hand, am I able to exert a force on it? No. If I was to do this in outer space, what would happen to this ball? It keep on going at whatever speed I gave it. Does that make sense? But gravity's like, no, 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 no. Causing it to slow down. The fastest it's going is right here. Does that make sense? Some of you just changed your paradigm of how you thought the world worked. Capture that. Okay? Last question. Tell your neighbor. Okay. For the sake of time, it would have been a good conversation. But at the highest point, did gravity, the force of gravity, turn off? Take a vacation. No, it's not no. It's still experiencing the force of gravity causing the acceleration of gravity. Okay? Here's another thing. How fast is it going at the highest point? 0. How long is it going 0 meters a second? Just a moment, just an instant. The moment right beforehand, was it moving? Yes, going up. The moment afterwards, is it moving? Yes. Which way? Down. From moment to moment to moment, is velocity changing? Yes. Meaning you have acceleration. Have a worksheet due tomorrow.